Hello, my name is Rüdiger Stirnberg. I have nothing to disclose. I am a physicist and MR sequence developer by training, so my talk is going to focus very much on the acquisition details of state-of-the-art echo-planar bold. But first, what is bold? Bold is a blood oxygenation level dependent contrast observed in the gray matter upon neuronal activity, more specifically, in the proximity of blood vessels. While a locally very specific type of bold contrast can be observed in T2 weighted images, this presentation only deals with the T2 star bold contrast, which is more widely used because of its higher sensitivity. The hemodynamic response upon a single event is several seconds long. Therefore, in order to properly probe the bold signal in response to multiple realistic events, we need a T2 star weighted time series acquisition, usually with whole brain coverage, with a few seconds of volume repetition time at maximum. Nowadays, even a sub-second temporal resolution is often preferred. The typical spatial resolution should not be larger than 3 mm isotropic. Gradient echo-planar imaging fulfills these requirements. EPI is well known to have a high signal acquisition time to volume repetition time ratio. Because optimal echo times are in the order of 20 to 40 milliseconds, usually all k-space lines of an image slice can be acquired in one go following a single excitation. The time spent on excitation, phase encoding, and gradient spoiling is relatively small. However, this comes at the cost of some serious downsides, most of which have to do with an imperfect shim or with the off-resonance of fat, for instance. And of course with the fact that even the best scanner hardware cannot apply infinitely short and large gradient pulses. This results in a low phase encoding bandwidth and thus strong phase evolution along the entire readout. The speed, the efficiency, and the artifacts of EPI depend on several sequence parameters. Because many of those parameters are highly interrelated, protocol optimization can become very tricky. Luckily, parallel imaging is an effective means to improve on many of those issues in state-of-the-art EPI. Before we go into parallel imaging in EPI, a brief visual toy example of how EPI works. All 9 slices of our example are excited and the corresponding 2D k-space data acquired in rapid succession. The slice order can be optimized to reduce unwanted saturation of neighboring slices. This goes on until the time series is finished. Although it is more rarely used, I also want to demonstrate a 3-dimensional echo-planar imaging variant, because it may be helpful later on, and because I spend a lot of my sequence developing time on 3D EPI. Like in the 2D EPI example, 9 k-space planes are acquired following 9 respective excitations. Unlike 2D EPI, the excitation affects the whole brain volume and spatial slice encoding is performed by a classic secondary phase encoding along the slice direction. Because each k-space plane corresponds to a new excitation, we have no geometric distortions along the slice direction. So 2D EPI and 3D EPI have a lot in common, but they are not the same. You may already have heard of simultaneous multislice imaging. In our example, a group of 3 slices is excited at the same time, and the signal corresponding to all 3 slices is acquired at the same time. This is repeated for all slice groups accordingly. This means if we don't do something about it, the images of 3 simultaneous slices will be superimposed in each slice group. One thing we could do is repeating the slice group excitations, which essentially is a small distributed volume, and applying different phases to each slice in the group with each excitation. This way, we can later on combine the signals in a way that the slices can be separated. A classic approach to this would be Fourier encoding. Now only 3 phase encoding steps would be necessary to disentangle the 3 slices by Fourier transform. You may already have realized by now that this is starting to have more in common with 3D EPI, although the excitation pulses are still very different, as well as are the times between the repeated excitations of the same volume. Either way, we have not achieved any acceleration yet. If we simply skip some of the slice encoding steps, we just end up with aliased images. This is where parallel imaging comes into play. Parallel imaging unfolds aliased voxels upon violation of the Nyquist-Shannon sampling theorem, utilizing the spatial information of multiple receive coil sensitivities distributed around or across the object. Whatever reconstruction algorithm is used, the image signal-to-noise ratio is going to be reduced by two factors: the square root of the total reduction, or undersampling factor, also called acceleration factor, and the coil geometry factor, G. If you are familiar with the simultaneous multislice literature, the SNR formula on the left may look more familiar to you. This is because, naturally, a different baseline SNR, the SNR of a single slice, is assumed. The additional scale factors E reflect the steady states for different repetition times and flip angles, which are often ignored, but this is okay if the repetition time stays relatively large compared to the longitudinal relaxation time T1. Anyhow, in SMS imaging, the baseline volume SNR is in fact increased by the increased number of simultaneously excited slices compared to the single slice. The slice acceleration factor thus cancels out. This is fantastic, as it means, compared to single slice imaging, we can increase the slice acceleration factor without the square root SNR penalty. Only the steady state signal will be reduced a bit as the volume repetition time reduces with slice acceleration. For 3D imaging, on the other hand, the steady state is typically not altered by the slice acceleration, but it is smaller and the square root SNR penalty definitely stays in the equation. However, to bring this in the right perspective, the 3D baseline SNR is quite a bit larger than the single slice and SMS baseline SNR. Doing a little bit of math, one can actually show that using Ernst angles, the SMS steady state will never be more than square root of number of slices over slice acceleration larger than the 3D steady state for the same volume TR. Therefore, the final SMS SNR will always be smaller than the final 3D SNR, but only a little bit for typical volume repetition times in fMRI. Also, there is more to SNR in time series acquisitions, as we will see later. Having discussed the square root acceleration factor SNR penalty, it is now time to also focus briefly on the geometry factor. The geometry factor reflects the ability with the used coil configuration to separate pixels superimposed by aliasing. Large values are bad, best values are around 1. The appearance of the G-factor map depends on the reconstruction algorithm used, but foremost it depends on the array coil and the k-space sampling pattern used. The influence of the sampling pattern can be understood if you consider how many voxels are going to be aliased on top of each other. You can make use of the binary aliasing cell concept to predict the appearance of an aliasing pattern. For instance, with a simple 2x2 undersampling pattern and a relatively tight field of view, there are quite a few voxels superimposed according to straight vertical and horizontal field of view shifts. A slightly modified sampling pattern and the aliasing pattern changes as well. This kind of diagonally shifted sampling is known as controlled aliasing in parallel imaging, results in higher acceleration, or short, caipirinha, or even shorter, CAIPI. Caipirinha is very important for state-of-the-art echo-planar imaging. Concluding the parallel imaging excursion, you can stop the video at this busy slide if you need some more references that are all very important and interesting to the whole topic. Okay, moving on. back to our EPI. We actually don't need the readout direction in these k-space views. In conventional EPI sampling, only the y-gradient blips define the k-space trajectory between readouts. Once finished sampling, the undersampled data is reconstructed using an appropriate parallel imaging method. You see that, apart from excitation and phase encoding preparation pulses, the sequence diagrams and the k-space sampling views are more or less the same. We can now focus on a single generic sequence type and k-space view. Now probably this simple 1/3 times undersampled acquisition does not lead to the best G-factor map. A CAIPI type sampling would be better. In EPI, this blipped CAIPI sampling is realized by introducing slice blips between readouts, and as a matter of fact, in most cases G-factor maps do improve. Sometimes the inverse of the G-factor is displayed, so larger values are better, as in this original example. Today blipped CAIPI EPI is widely utilized for rapid functional imaging. For very high resolution fMRI, it can make sense to approach CAIPI sampling without slice blips and larger Y blips instead. This has recently been demonstrated for sub-millimeter bold fMRI using dedicated high-density receive arrays. Note that this shot-selective sampling can be interpreted as simply skipping all blipped CAIPI samples that are not on the same KZ value as the first sample of the trajectory, and acquiring the skipped samples in subsequent shots. It is just as well possible that fewer or more blipped CAIPI samples can be skipped to achieve larger or smaller EPI factors, or smaller or larger Y blips respectively. Note, however, that generally all other sampling approaches but blipped CAIPI applied to simultaneous multislice imaging are no single-shot approaches. Blipped CAIPI applied to simultaneous multislice EPI is still a true single-shot acquisition. As you may have noticed, the images show no G-factor maps, but so-called TSNR maps, and the same maps divided by the respective square roots of volume repetition time. The temporal or time series SNR is given by the voxel-wise time series mean divided by the voxel-wise time series standard deviation. TSNR is always smaller than the hypothetical image SNR due to physiologically induced signal fluctuations that are known as physiological noise that scales with the available MR signal. As a matter of fact, the inverse of the proportionality constant lambda is the asymptotic TSNR limit. In other words, no matter how large one tries to drive the image SNR, for instance in a phantom scan, the actual TSNR in vivo will not exceed the asymptotic limit. In the thermal noise-dominated regime, on the other hand, TSNR still almost linearly increases with the SNR. Most high-resolution fMRI experiments are thermal noise-dominated. But even with large voxels, one can move towards the thermal noise-dominated regime, for instance by carefully increasing parallel imaging acceleration. (3D EPI is known to suffer more from physiological noise than 2D EPI. On the other hand, to the best of my knowledge, 3D EPI still offers more unique acceleration techniques as an alternative to parallel imaging than 2D or SMS EPI. This means that one can get the same temporal resolution with 3D EPI as SMS EPI without increasing the total parallel imaging acceleration factor too much. Why is that? Foremost, with 3D EPI, short composite water excitation pulses for fat suppression are straightforward to implement. Even single spectral selective pulses with extremely low specific absorption rate are possible. SMS EPI, on the other hand, mostly has to rely on conventional fat saturation. This has to be applied before each slice acceleration and results in about 20% increase of the volume repetition time, which does not contribute to more signal-to-noise ratio. Furthermore, as a volumetric imaging sequence, 3D EPI can make use of elliptical K-space sampling, at least in the K-space half of late echo readouts. This can save up to 10% of time. Especially for high-resolution EPI, this becomes quite handy to help keeping the temporal resolution on an acceptable level. Similarly, slice partial Fourier sampling is possible. However, in this case you should critically check the actual resolution achieved and also watch out for increased signal dropouts. To show you that this is not just academic, I want to show some of the results of a piloting study that we conducted for a large cohort study in Bonn. For the resting state fMRI protocol, we were aiming at a temporal resolution in the order of half a second. The whole brain should be covered at a voxel resolution of 2.4 mm isotropic. For the SMS EPI candidate, we had to select a slice acceleration factor of 8 to accomplish this. With the 3D EPI, we were able to select a significantly smaller acceleration factor of 6 thanks to rapid water excitation and variable EPI factor. The SNR maps show the corresponding benefit already. The ratio of the TSNR maps makes this particularly clear. Besides a difference due to a different T1 contrast, a G-factor benefit in the center of the brain, where some deep gray matter structures are located, becomes obvious. Also in the cortical gray matter, we could show with high significance an increased TSNR with 3D EPI. This benefit becomes even larger if motion and nuisance regression is performed. Finally, one general benefit of lower acceleration factors, not mentioned so far, is that residual aliases after parallel imaging reconstruction are less likely to propagate to the function analysis results. However, this topic is very complex, depends largely on image reconstruction details, and I will only add a few notes on this in the summary of this presentation. As there exists no general answer on what's better or worse, what you should take away from this is that dedicated piloting is always a good idea, no matter what sequences and protocols you have in mind. Gray matter TSNR before and after nuisance regression is a solid first measure to get hold of the quality of a bold fMRI protocol, but it does not replace an actual functional analysis. You may also wonder, what is nuisance regression and why should I consider it? As explained before, respiration and heartbeat are the main sources to introduce physiological noise into fMRI time series. This can be observed well in the whole brain power spectrum of the time series, where the actual bold variations of interest are typically only at relatively small frequencies. But there are large peaks at the higher frequencies which correspond to respiration and heartbeat. There are methods to predict the signal fluctuations if heart rate and respiration are known, or to extract the corresponding fluctuation from the data itself. In a linear regression, these can then be filtered out, that is, the variance that can be explained by respiration and heartbeat is regressed out. The gray peaks in the plot show the external heart rate and respiratory rate recordings. Note that the heart rate is aliased to lower frequencies because the Nyquist sampling frequency given by the volume repetition time. This is one of the reasons why high sampling rates are nice to have in fMRI, to prevent the fundamental harmonics of physiological signals to aliase into the bold signal. The other reason is that, of course, higher potential bold frequencies can be analyzed in resting state fMRI, for instance. Either way, the red curve demonstrates how well nuisance regression is able to reduce such physiological noise sources. At high spatial resolutions, it is unlikely to keep the temporal resolution as high. This is partly due to finite gradient strengths and slew rates. Dedicated gradient coils and novel sequences may lead to interesting future applications. At small voxels, time series data is typically thermal noise dominated. One way to still have sufficient temporal SNR is to do fMRI at higher field strengths such as 7 Tesla or even higher. In this example, we piloted a 3D EPI protocol at 7 Tesla using skipped CAIPI sampling that corresponds to a Y-blip of 3 at a moderate enough parallel imaging acceleration factor of 7 to yield a decent temporal resolution below 3.5 seconds at 0.9 mm isotropic whole brain coverage. The TSNR level is higher at 7 Tesla compared to the equivalent 3 Tesla scan, despite a 60% smaller voxel volume. Another good reason to do fMRI at high fields is a higher T2 star and T2 bold contrast to noise ratio. 7 Tesla is not the limit. For instance, a few 9.4 Tesla scanners are already around for a while. Even an 11.7 Tesla prototype scanner is being set up near Paris, and even higher field strengths are planned. Of course, with increasing field strength, the battle against susceptibility-induced artifacts becomes more and more challenging. Alternative fMRI approaches to echo-planar bold imaging can be expected to become more interesting. Another massive problem with higher fields is specific absorption rate, SAR. Keeping multiband pulses in the SAR limits is already challenging at 7 Tesla. The low SAR pulses of 3D EPI may be even more beneficial at higher fields. At 7 Tesla, typical 3D EPI still has a lot of SAR headroom. This can be useful if alternative approaches to functional imaging are explored that need a fast imaging host sequence on the one hand and a contrast preparation with large RF power disposition on the other hand. Vasoimaging that is based on an RF-intensive magnetization inversion preparation would be one example for such an alternative approach. Before I close, I want to briefly give some recommendation on how to compare TSNR of protocols with different temporal resolutions in a reasonable manner. For this, it is sufficient to understand that the statistical power of fMRI time series analysis, roughly speaking, increases with the square root of the number of volumes in a fixed acquisition time, provided that the TSNR does not change by increasing the number of volumes. This essentially corresponds to precision improvement by averaging. It is convenient to simply normalize the obtained TSNR by 1 over square root of the respective volume repetition time. Note that the volume TR is typically inversely proportional to the slice acceleration factor, which thus kind of cancels out of the TSNR efficiency map. Efficiency very conveniently summarizes multiple metrics important for bold fMRI: coil sensitivity, total parallel imaging acceleration, G factor, physiological noise, etc., without knowing each of those metrics specifically. Therefore, it is optimally suited for ad hoc protocol comparison of different temporal resolutions with and without nuisance regression at protocol piloting stage. Again, however, it cannot replace a dedicated fMRI analysis that should also consider temporal correlations, etc. With this, I want to wrap up this presentation and repeat the most important things to remember. Foremost, parallel imaging is key to state-of-the-art echo-planar imaging. The most important technique to know and understand is blip CAIPI and corresponding parallel imaging reconstruction. Actually, there are several different approaches to reconstruct simultaneous multislice EPI data with very elaborate ways to minimize artifacts and keep SNR high. The SMS 3D K-space analogy I have used here for educational purposes, and frankly, because it helped me to understand the concept in the first place, is only one of them that can be applied to both SMS EPI and 3D EPI. Going into each of the methods is beyond this presentation, but it is useful to be familiar with the method implemented on your scanner vendor's image reconstruction system. Some general pitfalls to keep in mind. With strong acceleration, the G factor often increases rapidly. Also, residual parallel imaging artifacts are more likely to propagate to the fMRI results, possibly unnoticed. It helps to keep the total acceleration with standard coils at 8 or below when using caipirinha, and try to optimize the CAIPI sampling or field of view shift according to the actual coil and field of view used. What I have not mentioned so far is that state-of-the-art parallel imaging reconstruction also involves regularization and other parameters that may be worth modifying. Also consider a suitable parallel imaging calibration technique, which can lead to massive improvements in TSNR and artifacts. For these kinds of questions, I can only recommend the excellent blogs below by Ben Inglis and Renzo Huber as invaluable resources of practical fMRI knowledge. Finally, I want to repeat, a dedicated protocol piloting stage before your fMRI study starts is generally advisable. Temporal SNR and efficiency are helpful metrics. Don't forget to consider nuisance regression. Perform an actual fMRI experiment and analysis and decide on this basis what is a suitable protocol for your research question. With this, I want to close and thank you for your attention.